Hello students, we shall be talking about oscillating dipole in this lecture. Oscillating electric dipole. Now, an oscillating motion of a system is an accelerated type of motion, and acceleration is always associated with radiation. So when we're talking about an oscillation, it means there is an acceleration taking place, and the acceleration normally leads to radiation. Now, the magnetic vector potential denoted by A of a dipole is given as A is equal to mu 0 by 4 pi r p dot into nr cos theta minus n0 sin theta, where r is the distance between the two charges. So this is a positive charge and this is a negative charge. The distance between them is r. And nr is the refractive index of the medium, and n0 is the refractive index of vacuum. So we get three components of the magnetic vector potential A in terms of AR, A theta, and A phi. So in spherical polar coordinates, that is R, theta, and phi. R is actually not the distance between those two. R is actually a radiation, where we are actually calculating the radiation from the dipole. That position is considered to be as the R, and P is the dipole moment. So this R is actually the distance from the dipole. And by oscillating dipoles means these charges are changing their positions. The negative is going to the positive and the positive is going to the negative. Okay. Now again, as we have told, we are considering the spherical polar coordinates. So we would be writing E in terms of r, theta, and phi. R, theta, and phi, it's like this. This is the coordinate system. We consider this as zx and y Cartesian. So the spherical coordinate is, so this is the point, so this is r, and this is theta, and this is phi. So in that context, the value of ER is mu 0 by 4 pi r into P dot cos theta and A theta is minus mu 0 by 4 pi r to p dot sine theta, and this component is not existing. Now the distance between, if the distance between the two charges, if we take them as equal to dl, and the charges being plus q and minus q, then we get P is equal to q into dl, the dipole moment. Now, as we have said that the charges are oscillating, that means the plus and the negative charges are changing their positions. So there is an oscillation involved. So due to this oscillation, we can write that the charge q as equal to, let me write it here, the charge q as equal to q0 e to the power minus I omega t, then we can write P is equal to, as we have said, it is equal to q into dl, so this becomes equal to q0 e to the power minus I omega t into dl, and so if you write P0 is equal to q0 dl, then we can say that P is equal to P0 e to the power minus I omega t. Now a dipole whose moment varies sinusoidally, so this is what is being represented by this equation. The dipole moment is varying sinusoidally. So this is actually what is known as an oscillating dipole. And this oscillating dipole, it may be assumed to be an accelerated charge. Accelerated charge. And the distribution of the dipole moment can be written as P is equal to rho r dr dash dv dash, and the time rate of change of dipole moment, that is P dot, is equal to dp by dt, that is equal to, which is again ddt of q dl is equal to dl into dq by dt, and this is nothing but the current. This is dq by dt is the current I. So the value P is equal to I dl is the expression that is obtained. So so time rate of change of dipole moment is equal to the current element. Now this an accelerating charge or an oscillating dipole, it will always radiate energy. So as we have already seen here, and we have found out the vector potential. Now second, if we look into the scalar potential, phi, we get we have the following value: phi is equal to 1 by 4 pi epsilon 0 into p cos theta by r square plus p dot cos theta by r square. So from the expression we can say that the scalar potential phi, it varies as cos theta, and so its value should be equal to 0 in the equilateral plane. So in equilateral plane, value of theta is pi by 2. So cos 0 cos theta is equal to 0, and so the value of scalar potential is also equal to 0. There has been a mistake, I think. The value of the scalar potential this is not r squared, this is only r. Okay. So one of the part varies as in the scalar potential, one of the part will vary as r square to the power minus 2, another is to the power minus 1. So the one which varies as to the power minus 2, this part, this dominates for small values of r. Dominates for small values of r, and hence it is responsible for the induction field in the nearest zone. So it is also, I can say that, responsible for the induction field in the near zone. The one which varies as 1 by r, it dominates for large values, large values of r, and it is actually responsible for the radiation at large distances. Radiation field, responsible for the radiation field and the distance zone. Now, the magnetic induction in the case of oscillating dipole can be written as B is equal to 1 by 4 pi epsilon 0 into, again there are two terms. One is p dot sine theta by r square, and another term is sine theta p double dot r square. Now, again, so again we can, as in the case of scalar potential also, we can see that the value of B varies as sine theta. So the value of B will be equal to 0 for theta is equal to 0, and theta is equal to 0 will be along with equiaxial axis. This is exactly 0 along the polar axis. And highest value along the equilateral axis. Now, again, this 1 by r square dependence. This term is inductive or convective field. Whereas 1 by r, this is for the radiation field. So if we draw an analogy with the magnetic field, with electric field, we can say that before that we can show that B is equal to 1 by 4 pi epsilon 0 into I dl sine theta by r square into n into phi. Phi stands for the scalar potential, and phi. So we can include the value of scalar potential here, and we can say the value of B, and this is the Biot-Savart's law. Introduced here. If we draw an analogy with the electric field, this electric field has also got three components. One which is varies as 1 by r cube plus one which varies as 1 by r square, and one which varies as 1 by r. So this is the this field. This is the static dipole moment due to the static dipole moment, and it's a short range field. is due to static dipole moment. The arc square field is, as previously said, it is due to the inductive or conductive or Coulombic type, inductive, conductive or Coulombic field, and depends upon the steady current due to charge oscillations. And the steady current is important here due to oscillations of charge, and the capacity 1 by R is the radiation field, is for the radiation field, and it depends upon the time variation of current due to charge oscillation. So it depends upon time variation of current due to charge oscillations. So if we just consider the radial component of electric field, we will get E as equal to 1 by 4 pi epsilon 0 c square into P double dot by R square and by R into sine n theta. So it shows that it assumes the value, it varies as sine theta, and is a maximum value along the equatorial axis. So Emax along the equatorial axis, and how the equatorial axis will look like, I can show here. So this is the dipole axis, and this is the equatorial axis, and this is the angle theta.